Welcome to this video lesson. In this video, we will be exploring the second law of motion. The learning goal of this video is to state what the second law of motion is and to be able to use the second law of motion to solve problems and sometimes even explain certain situations. Let's talk about second law experiments and how we can collect data experimentally to come up with the second law of motion. And in this situation, this is also an introduction to kind of data collection and analysis. So how do we actually organize our data? What do we do? How do we write it down? How do we show sample calculation? So it's a mix of those two ideas. So in the following experiment, we have Mr. Shateri who is investigating the relationship between the applied force and the acceleration on a 0.5 kilogram mass. So there's obviously a whole design process that has been done here, but in summary, Mr. Shateri places a 0.5 kilogram mass on a surface with a negligible friction and applies various forces and measures the final velocity of the block after plus or minus 0.4 seconds. So that's anywhere between 3.6 to 4.4 seconds. He then uses the information to calculate the acceleration and its uncertainty and plots it. The experimental setup is shown in figure 1. Notice that I'm trying to write a little bit just like the way I mark your labs, and you can see that the experimental setup, at least the basis of it, is shown here. I would include more information, whether this is a table, what this actually is, but in this case, this diagram is pretty good. It has all the information that we really need. We have an object. You put a force on the object. The value of the force is unknown, so I'm not putting that one in. Initially, it has a velocity of 0. And later on it's going to have some other velocity. This is kind of what we're measuring, and that velocity is going to be bigger than v1 in terms of magnitude. And the displacement here we don't know. We don't also need to know it. The time is 4.0. That's 4.0 plus or minus 0.4 seconds. So there's about 10% uncertainty on the time. And the mass is 0.5, and our units are kilograms per mass times a second, and our length is in meters. That makes our velocity meters per second and our acceleration meters per second squared. And in this case, the information that we have are time, initial velocity, and we're going to measure velocity too in order to calculate the acceleration. Note that this surface is also almost frictionless. Note that I also said that the experimental setup is shown in figure 1, and figure 1 says that this is the experimental setup. So you need to make, whenever you have a figure, you need to label it, you need to have a summary of what that is about, and in your text, you can give more information. So you can say the experimental setup is shown in figure 1, and then you can give more information if you need it. I just explained it to you, so I didn't write them all down, but you can write that initial velocity was 0, velocity later was bigger, that's what's measured, and so on. Okay, let's keep going. So that was the experimental setup. I'm going to zoom in slightly here and go all the way. Okay, so you can see the experimental setup there. Fantastic. So the raw data is whatever you collect. Along with the sample calculation are shown in table 1. So there's some process data. I should have said raw data and some of the process data. But table 1 has the information that I need. So we can see that our independent variable is the force. You can see that I have the uncertainty of my force, that's plus or minus 0.2 newtons. And because force is vector quantity, I also have the direction. And you can see that I have the values 0, 1, 2, 3, 4, 5. I've chosen 6 values. We need at least 5 in order to kind of see a pattern really clearly. So I got all those 5s plus their uncertainty. For the final velocity, I've done it 3 times. You can do it more than that. So you can do 4, 5 if you want to. don't do it too many times, but 3 or more is necessary. And you can see that my final velocity also, every time I measured it, it had 0.5 meters per second of uncertainty, and that's the direction of my final velocity. And for each trial, I have written the numbers. And note that, as you can see, for both my force and final velocity, they had the uncertainty written in one decimal place, and all my measurements are also written in the same number of decimal places. And that's very important because your uncertainty and your measurements need to have the same precision because they all come from the same measuring tool. So I would call everything here raw data. Those are all the information I've gathered from my experiments. And then I'm performing some processing. I'm doing some processing in order to find the average velocity final and its uncertainty. So I need to show some sample calculation of how I came up with those information. And I'm going to do that on the side here. So I'm going to start off with sample calculation, and I am going to do this for, you can choose which force. I wouldn't do it on 0 because for 0 it's just been 0. Nothing really has happened for that one. And I didn't have to collect any data, so I'm going to say for force of, I'll just do 1 Newton here. The average velocity was calculated by adding all the individual ones, so 7 plus 8.2 plus 8.4, and I divided that by 3, and that ended up being 7.866, and I'm taking right to be positive here, so I can write that out. I don't really have to if I have a diagram somewhere there, but it's nice if I do write it. And that would be approximately, I need to figure out how many decimal places I'm going to go to. And I can see that every calculation that I had was 1 decimal point in this case. And since then I'm not going based on number of significant figures now, I'm going based on decimals. And since all the values had 1 decimal places, I have to have, my final measurement can't be any better than that. So this is approximately 7.9, and my units meters per second, and my direction to the right. I also have to show how my uncertainty was calculated. So from my uncertainty was calculated using max minus min divided by 2, and you may use another formula or another way of calculating this. But my max number here was 8.4. My lowest number was 7.0, and I'm dividing that by 2. And when I do that, I will get exactly 0.7. So if this was also 0.7 something something something, you would have to round it. But in this case, it's just the 0.7, and both of my measurements and their uncertainties need to have the consistent number of decimal places, and you can see that they do here. And this is beautiful because I've shown exactly how I have come up with my average velocity and uncertainty, and I only have to show it for one value. It's actually not concise. You would lose marks for your work being not concise if you show more calculations. And we can see that basically this is very interesting actually. So you can see that every measurement that I took had an uncertainty of approximately 0.5 meters per second. But let's say for force of 4, or anywhere between 3.8 to 4.2 based on that uncertainty, I get these values. And if I had just gotten one value, and if I didn't repeat the experiment, I would have to choose the value of 30. But after taking a few, I realized that my average is 32, and I realized that my uncertainty is pretty high too. This is a much higher uncertainty than my original one. So repeating the experiment does help me get a better gauge about the uncertainty of my work. You can also see that my uncertainty is actually increasing as the forces are increasing, and that would actually make sense in this type of situation because it's going to become a lot more difficult to measure the velocity when the forces are higher. Okay, so now I have processed some of my data, and then I'm going to go ahead and I'm going to show you both tables here, or as much as I can. Okay, I'll go right here. Mr. Shateri then processes the data to calculate the acceleration of the block for each force. The results and the sample calculation are shown in Table 2. So you can see that, again, Table 2 is mentioned in text, and then Table 2 is the process data and sample calculations. Okay, so I need to show a sample calculation for at least one of these, so let's do that. And for the uncertainty, just in this video, I'm not going to show how I did it for this particular case because it's different for all. So that you should be writing how you calculate your uncertainty, but I'm just going to show you how I calculated acceleration here. And let's do that here. I'll write in purple. And I need one sample. So sample calculation. And you get to choose which one you're going to do it for. So I'll do it for, let's say, the same one. Let's do for force of 1.0 plus or minus 0.2 newtons. I should have written my direction in the last one as well, so I'll do that here. The information that I have here is the initial velocity, so that's given to me from the initial question or initial setup, experimental setup. The time that I used was 4.0 plus or minus 0.4 seconds. The velocity that I measured was equal to, I'm going to use the average one here, that's 7.9. And I would have to use the exact value actually, so this is approximately 7.866 plus or minus approximately 0.7. And what I'm trying to find is the acceleration. So when I have these information, I have velocity 1, initial velocity, final velocity, the change in time. And what I don't have is the displacement, so I need to use the equation of motion that doesn't have displacement in it. That equation is V2 is equal to V1 plus A delta T. And I'm taking right to be positive here. And velocity 2, I'll plug it in, 7.866 is equal to my velocity 1, which is 0, plus my acceleration multiplied by the change in time. And, the change in time is actually 4 seconds. You don't have to write the uncertainties when you're doing this step. You're just finding the actual measurement. So this is going to be 4. And when I rearrange this, I'm going to get A is equal to, and when I divide 7.88 by 4, sorry, 7.866 by 4, I get 1.966 repeated, and that ends up being approximately, I have to round, so my final answer in this case, now that I'm doing these set of calculations, since I'm processing, I do need to start looking at the number of significant figures, and my lowest is 2 throughout all of my calculations. So for my final answer has to be rounded to 2 significant figures. In this case, I have to round up. This becomes a 0, this becomes a 2, this becomes 2.0, and my unit is meters per second squared, and my direction is to the right. And that's how we would calculate our acceleration, and obviously that needs to be consistent with your acceleration in here. And in this video, I won't show the sample calculation for the uncertainty. That requires a little bit of space and different sets of knowledge in order to be able to do that. All right, so basically in this process data, note that I have the force, I have my uncertainty for each one. Which is 0.2. I have the direction for the acceleration. I have the unit. I have the direction. These are the values for it. And I don't have the uncertainty here because I have another column which is showing the uncertainty of acceleration. And I'm showing that it's plus or minus, and my unit is meters per second. Oh, this should say meters per second squared, so I missed that. That needs to be a 2. All right, let's go to the next page. Once I have all the data, I'm gonna plot them, and let's look at our plot. So first of all, the results are plotted in figure 2. That's beautiful. All the information is there, and then I have figure 2 here. Figures are usually labeled below the figure, and tables are usually labeled above the figure. Note that this figure is the relationship between acceleration and force acting on a 0.5 kilogram block. So since I will have the label of my figure right here, I don't have to include it here. In fact, I don't want to label it there because then I'm double labeling my figure, and I don't want that. So whatever this label should be, that goes in here, and you are just going to say in your text that the results are plotted in there, and then kind of when somebody is reading it, they're like, okay, the results, which is the relationship between acceleration and force acting on a 0.5 kilogram block, are shown in figure 2. Now, what is included in here? Note that on my y-axis, I have my acceleration. That's my dependent variable. That's what I've been measuring. And my independent is the force measured in Newton, and the direction is here. And even for my acceleration, I have the unit here, and I have my direction there. And I'm using forward instead of arrows because I can't draw the arrows when I'm using my editing tool for Excel. Okay, now in terms of the dots, you can see that I have all the points. So that's the acceleration at 0. These are the acceleration at 1, 2, 3, 4, and 5. And you can see that I also have error bars. I have the error bars for force because the error in them is 0.2. So remember that for 1 is anywhere from 0.8 to 1.2. For 2 is between 1.8 to 2.2. And for 5 it is 4.8 to 5.2. So these error bars show that set of information. And for my acceleration, I also have those errors plotted. 0 didn't have any error bars because for 0, I basically took the exact, it was just 0, there was no calculation. If I didn't move it, velocity 2 would be 0. That's a kind of like perfect calculation, or it comes from calculation rather than experiment. In this one, for 1, you can see I have the error of acceleration, and the errors are actually changing. You can, if I know that I'm doing this in Excel, and in Excel I have the ability to do different errors for different points. I know that in Google Spreadsheet at the moment, and for many years, I don't know why they haven't added this feature yet. You cannot do that at the moment, so you can only choose one value. And if that's the case, then what you want to do is you want to choose the maximum value. So you can choose, just see which one is max error, this or this, and then choose that for all of the different cases. because you can never go with your lowest, you always need to go with your highest. But this is very nice because it does bring another discussion point for us, and the discussion point is that we have to discuss later in the lab is why is it that the error for uh, accelerations when I was calculating it for force 1 is much smaller than the ones for 5. So again, something to talk about later, but it's actually really cool that this actually happened during the experiment. Okay, so this is the graph. These are some discussion points you could actually have for this graph, or this relation. And sorry, before I go on, I gotta also mention that there's the r² value for the graph it's here. And this value is very close to 1. And whenever r² value is very close to 1, it means all of the points are very close to the line of best fit. And in this case, you can see that the line of best fit is pretty much almost touching most of the points here. For sure, it's going through all the error bars, which is fantastic, but it's definitely very close, and that would mean that the r² is 1, and that means it's a strong correlation. This is the equation for the line, so you can see that y is equal to 2 points, and this comes right from Excel, 2.0286x minus 0.0437. My y is the acceleration, so this means acceleration is equal to 2.0286 times my force, because that's my x, minus 0.0437. You can notice that my y-intercept is extremely small. It's very close to the value of 0, and that's good. Also note that I have 6 points, so it assures me that this is a linear relationship, because if I had more points, it would even be better. But if I only had 3 points in my graph, then let's say I didn't have these and these, then if I only have 3 points, I wouldn't really know, because it could be a relationship like this, it could be a relationship like this, or it could be linear, or some other sort of relationship. So you need to have at least 5 different points to kind of see that pattern. Okay, so those are all the information that I get from my graph. Some of the discussion points here could be large uncertainties for both acceleration and forces. You can see the uncertainties are pretty big. In general, the increase in uncertainty of acceleration, what I talked about, that's a very good discussion point for later on in the lab. The coefficient of determination, so that's r² value, so you can talk about the fact that it's very close to 1, and that's a good thing. That means the relationship or your points are very close to the line of best fit, and that it's a strong relationship. The relationship itself, so in this case, well, we'll talk about it in a second, and prediction of what will happen if there were larger forces. So our experiment is only limited to about 5 different values. If we were to interpolate here, then values in the middle will probably lie somewhere within this line. But if we went further and further, would the relationship start curving, or will it still go straight? Those are nice discussions that you could have, and there's other things that you can discuss as well. So going on, in terms of the coefficient of determination, we can see again, since this value is very close to 1, it means that most of the data points are very close to the line of best fit. This is an indication of a strong linear relationship between the acceleration and the force. More data points are required to ensure that this is true for larger forces. So you can see that I'm not claiming that this is going to work for all the values based on my experiment. We need to do more. We need to get more information in order to test those forces. The relationship itself, you can see that the acceleration and force are proportional, and we've done this before. For a relationship to be proportional, there needs to be two main, it needs to satisfy two ideas. One is because the line of best fit that goes through all the error bars is straight, and it passes through the origin. So those are the two conditions that they need to satisfy. It needs to be a straight line, and it needs to go through the origin. And you can see that for ours, it's not touching the origin exactly, but it's extremely close. So within it, the uncertainties, it would have passed through the origin. Now, that kind of concludes what I wanted to talk about in terms of the lab part. So in terms of lab, in your next lab, you pretty much have to collect your data, start plotting it, start finding your uncertainties, and come up with a graph that looks like this. And it has the uncertainties, it has the line of best fit, and then kind of talk a little bit about the graph and the relationship. Is it proportional? Is it not proportional? If it's not proportional, how does the relationship look like? So how does the force actually affect the acceleration and so on? So those are some of the points that you're going to talk about. In this relationship that we found based on these set of information, we're seeing that the acceleration and the force are proportional. So how do we write that mathematically? Let's talk about it. In this particular situation, we have a graph of acceleration and force. I'm not going to write the units here. And the relationship here is proportional. It means that it goes through the origin and it's a straight line. If you want to find the equation for this equation, actually before that, since they're proportional, we can say that acceleration is proportional with the force, or that force is proportional to the acceleration. In this case, if we were to redraw this as force and acceleration, we would actually find out that it also follows the same pattern. It's still a straight line and it still goes through the origin. So this is how we say two things are proportional, and it just means that if we were to plot these two set of information, we would get a linear graph that goes through the origin. Let's focus on the second one right now. Force is proportional to acceleration. That's this one. And let's come up with an equation for the line of best fit based on this. To find the equation of line of best fit, when it's a linear line, the equation of the line is always y is equal to mx plus b. I'm going to write that with purple. So y is equal to the slope multiplied by x plus the y-intercept, which is b. Now, we can see that the y value here is the force and the x value here is the acceleration. So instead of y, we can write that force is equal to the slope multiplied by our x, which is the acceleration, plus b. And in our case, the b value or the y-intercept, because it's proportional, is just 0, so we don't actually have to include anything here. And this would actually mean that the force is equal to our slope value, whatever that is, multiplied by a. If I look at my graph that I just did, actually, let's look at it here. We can see that the relationship was about the acceleration and force. I'll just write it out here. Acceleration was proportional to the force. That means acceleration would equal to some sort of slope value multiplied by the force. And my slope value in this particular case was actually approximately 2 times the force. And if I were to rearrange this for force, I would get force is equal to 1/2 multiplied by acceleration. So all I'm doing here is I'm dividing this side by 2 and this side by 2. So this side by 2, I will get force. This side divided by 2 is 1/2 times the acceleration. 1/2, this is an important value. And in my lab, when I was collecting the data, value of 1.5 was actually my mass. And that's actually pretty interesting. So in this case, I'm finding that the slope of this graph, or the slope of a force and acceleration graph, is actually the value of the mass. I'm going to go down and write that first. So in this case, we have force is equal to our mass, which we just found multiplied by the acceleration. Very, very cool. Now, in order to kind of make sure that this always works, I have to repeat this experiment for other masses and make sure that it will always be the case, because maybe this was just luck, and I gotta make sure that it's always true. So I would have to repeat this experiment for all the masses and kind of make sure that it always happens. But in this case, based on my finding, the force is equal to mass times acceleration. And this is actually true if we were to repeat it with other experiments or different masses. And this is our simplified second law of motion, which states that force is equal to the mass of an object multiplied by its acceleration, or the net external force acting on an object is mass times its acceleration. And the other ways of writing this is force is proportional to acceleration, or acceleration is proportional to the force. Any of these actually work. The slope here is the mass. That would mean that if I increase the mass, so this is mass 2, which is bigger than mass 1, and this is mass 1. So if I were to increase the mass, my force would be much larger for the same acceleration. And if I were to reduce the mass, then the force that I have to put will be much smaller for the similar amount of acceleration. This mass value is our resistance to change. And remember that we talked about this already. We talked about inertia being a property of matter that resists the change in motion. Well, the change in motion is acceleration. And if I put a certain amount of force on an object, then if I were to rearrange this, actually, let's do this. Let's talk about it. Acceleration is equal to 1 over m times the force. So let's say I'm consistently putting a force value of 1. I'll just write force is equal to 1, and I'll put different mass values, 1, 2, 3, and 4. And you can see acceleration. If I put a mass value of 1 in here, 1 over 1 times 1 is just 1. If I put a mass value of 2, it would be 1 divided by 2 times 1, which is 0.5. If I put 3, it's 1/3, or 0.3. And if I put 4, it becomes 0.25. So the larger the mass value is, the smaller the acceleration. And the smaller the acceleration, the smaller the change in velocity that we're going to have, and smaller amount of change in motion. So the mass is representing our inertia here, and the more inertia that we have, the more resistance to change we have, or change in motion, and therefore you can see that the accelerations are reduced as the mass is increasing. Good. So let's summarize all of these down here. So in a simplified version of second law of motion, this states that if the net external force acting on an object is not 0, the object will accelerate in the direction of this net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. It is mathematically represented as Fnet is equal to mass times acceleration. The implication of Newton's second law are: objects with net external force acting on them will cause them to accelerate in the same direction. So that means if there's a net external force, if my object has 2 forces acting on them, and this is bigger, the net external force is this way, and therefore the acceleration is also in this direction. And if it was the opposite, the acceleration would be in the opposite direction. The acceleration of an object results from a change in speed or change in direction. So we already actually knew that. And the object's mass will affect the acceleration. The higher the mass causes a lower acceleration and vice versa. And that's kind of the link to inertia, which is the property of matter that resists the change in motion. And the higher that inertia, the lower the change in motion. In general, we can write that if there is an unbalanced force acting on an object, then this force can be calculated from the product of the object's mass and its acceleration. So that's kind of repeating the information here, but in another set of wording. It is important to note that this direction depends, this is direction dependent, so you can do your calculations in the x direction and y direction separately. So you don't combine all of these. This is the simplified versions of Newton's second law of motion. Later on, we will learn the complete version of the second law of motion, and this usually happens in the Ontario curriculum. It happens in grade 12 when you learn about momentum. Let's do some examples. The new equation that we've just learned is that the net force acting on an object is equal to its mass times acceleration, and that's what we're going to use. In this first situation, we have a mass which is 3 kilograms. There's two forces acting on them. The force 2 here it's got a magnitude of 5, and the force here has a magnitude of 15. And in terms of vectors, let's take a direction to be positive. I'm going to take right to be positive for all of my calculations. So if I'm writing force 1 as a vector, I would have to write it either as 15 is pointing to the left, so it's either negative 15 Newton to the right, or it is 15 Newton to the left. I'm going to try to use everything to the right as positive. And force 2, that's 5 Newton to the right, so I can just write it as 5 Newton to the right. Write it as 5.0. The net force, so to find the net force, there's two different ways of doing this. One is to just subtract the two forces from each other, so and that's what we have to use because we don't have the acceleration yet. If we did have the acceleration, we can just multiply mass times acceleration, but we don't have the acceleration. So to find the net force, I'm going to subtract all the forces that are going right by the forces that are going left. So this is going to be F2 minus F1 in terms of magnitude, or I'll just write it as F2 plus F1 in this case. Because I want a vector quantity, and F2 is positive 5, and F1 is negative 15. So this is going to be negative 15 newtons in the right direction. To find the acceleration, I'm going to use my new equation, which says Fnet is equal to mass times acceleration. So Fnet here is negative 15, and that's equal to the mass, which is 3 times acceleration. Divide both sides by 3, and I get my acceleration is equal to negative 3 meters per second squared in the right direction. And note that I'm doing everything to the right. And this is my final answer. Let's do one other example in this direction. We have our mass. We got force 2 acting in that direction, force 1 acting in this direction. And do we even have enough information? Well, maybe. We're told that it's uniform motion, and if it's uniform motion, that means the forces are balanced, so these two values must be the same. So if force 1 has a magnitude of 15 Newton in this direction, if I'm taking right to be positive, its vector quantity is going to be negative 15 Newton to the right. The net force, well, if it's uniform motion, that means that that means that this force and this force are the same, and if they're the same, that means that Fnet is 0, because if I subtract this value from this in terms of magnitude, I will get 0. Acceleration, if it's uniform motion, that means that its velocity isn't changing, and therefore acceleration is also 0. So this is 0 Newton right, this is 0 meters per second squared to the right. And how do we find force 2? Well, we know that force 2, then Fnet is going to equal to force 1 plus force 2. And F1 has a value of negative 15, Fnet is 0, and this is F2. So F2, when I rearrange it, is going to be 15 Newton to the right. So its magnitude is just going to be 15 Newton, and I'm going to highlight this, and its vector quantity is going to be 15 Newton to the right. So that's the value for this one. And that's how we use second law of motion. So basically, we look at the diagram, we see what information we have. If it's uniform motion, our acceleration and net force are 0, it simplifies our question a lot. If they're unbalanced, then we have to find net force. If we have both of the forces, we'll just use those to find the net force, and then to find the acceleration, we use the equation. If we're given the acceleration, then we will use the acceleration to find the net force, and then if we're missing any of these information, then we are going to use our Fnet is equal to the sum of the forces to find those forces. So again, in this situation, we have to use the idea that Fnet is equal to sum of forces, and it also equals to mass times acceleration. And that's what we're going to use in this unit. Okay, the other idea that I need to cover for this part of this lesson is weight versus mass. So the measurement from a spring scale shows the weight of an object. The weight, shown usually by W or Fg, of an object is its mass times the gravitational acceleration, or the gravitational force that acts on an object. Note that weight is equal to the gravitational force. You can use W for it, you can use mg, you can also use Fg. Note that scales measure the normal force on them, so I'm going to highlight this as well. Very important. I'm going to write this: weight is equal to mass times gravitational acceleration. This is also written like this, and sometimes written like this. Note that this is also just the magnitude, and we're not actually using a direction. So this is G. G is only a magnitude. Usually, if you're writing it as a force, we will also indicate which direction it's acting in. The other thing that is mentioned here is that if you have a spring scale that measures your weight, what it actually does, it looks at whenever you're in contact with it, there's a normal force acting on you, and from the scale to the person, this is the force that's measured by the scale. So use the formula that you have just found to calculate the weight of a 7-kilogram object. So W is equal to mass times G. And the G value, I forgot to mention, is the gravitational acceleration. And on Earth, G is approximately 9.81. So this is going to equal to 7 times 9.81. And this is going to equal to 68.67. But I'm only good to one significant figure here. So that's 70 Newton for my final answer. Okay, let's do another set of examples just to get a much better idea about weight. And each of the following force diagram represents different problems. From the given data, solve the missing quantities and assume that the value of gravitational acceleration here is 10. So we're going to simplify the calculations a little bit. Okay, let's do this. Weight, or Fg, for the very first one, we can see that the mass of this object is 1. So the weight is going to be mass times the gravitational acceleration. So that's 1 times 10. Note that we said 10, use 10 here. So that's going to be 10 newtons. We're not asked for the vector quantity, so I'm not putting up or down here. The acceleration is 2 meters per second downwards. Okay. I'm going to indicate that here. That's 2. Acceleration is 2. And I'm going to take up to be positive for my calculations. So Fnet is going to equal to, well, in this case we have the mass and we have the acceleration. And this is going to be mass times the acceleration. My mass is 1 kilogram, and my acceleration is 2 meters per second downwards. I'm taking up to be positive, so I have to use a negative value here. So this is going to be negative 2 Newton upwards. I need to find the value of the force. So Fnet here is going to equal to, so there's two ways of calculating Fnet. One is mass times acceleration, and the other one is sum of the forces. So this is going to be equal to the force plus Fg, and these are all in vector quantities. So the force is what I'm trying to find. Fnet has a value of negative 2. Put that here. That's going to be F plus Fg. Fg is acting downwards opposite to this, so instead of putting a positive value, I'm going to put negative when I'm using vectors. So that's negative 10. And if I were to rearrange this, I would get that force is equal to negative 2 plus 10, or 8 newtons upwards. And that would mean the magnitude of F is just 8 newtons. Looking and just making sure this works really fast in our head, this force is 8, this one is 10, so 8 minus 10 is negative 2, that's the net force, and that's good. If it's negative 2, then negative 2 divided by the mass should give us the acceleration, which is the case here. Okay, in our next example here, I'm going to use a different color so we can see things a little bit easier. We got a mass of 6 kilograms, so we can find the weight really quickly. That's 6 times 10. Again, I'm using the 10 because of this. Usually I have to use 9.81, and this is going to be 16 newtons. And that would mean the vector quantity of Fg, if I were to take up to be positive, would be negative 60 newtons in the upward direction. The acceleration this time is 4 meters per second acting upwards, and to find Fnet, that's mass times the acceleration. Mass is 6, acceleration is 4, positive 4 because I'm taking up to be positive, and yeah, and this is also acting upwards. And this is going to be 24 Newton in the upward direction. Then I want to calculate the force. You can do this in different ways, so actually I'll show you both ways. One is what we used last time, which was Fnet. You can write it in terms of vector forms. And for vector, we got Fnet is equal to sum of all forces. So, sorry, that's just Fg plus F. Fg is 60 Newton, negative 60 Newtons. And F is what we're trying to find, and F net is 24 newtons upwards. So if I were to rearrange this, I would get F is equal to 84 newtons upwards, and therefore magnitude of F is just equal to 84 newtons. You can alternatively do this with just concepts, and Fnet in terms of its value, if we're taking up to be positive, is going to equal to 24. I'll write the values in a second, but Fnet is going to be whatever this force is subtracted by this force in terms of magnitude. So this is F minus Fg. Note that I'm not using vectors anymore. I'm just using concepts and the fact that whatever the Fnet is, it's going to equal to the force acting upwards minus the force acting downwards. So Fnet 24 is going to equal to F minus the value of Fg, not its vector, but just its value, which is 60. And if I were to rearrange this, I would get 84 Newton. And that is my final answer using both methods. And we'll stop this part of the video. We're going to call this part 1 of the video, and we're going to do part 2 on a separate video, and we're going to do some problem solving with second law of motion there.